Welcome back. Now we will discuss the Chapman-Kolmogorov equations for CTMCs. Okay, the Chapman-Kolmogorov equations deal with a quantity Pij of t, which is defined as the probability that the process CTMC at time t is in state j, given that the process at time 0 was in state I. Okay. So, given that the process started in state I at time 0, what is the probability that time t the process will be in state j, alright. This is Pij of t. So, this plays the role, same role as Pijn for DTMC, right. So, Pijn is the probability of being in state j after a long time, after some time n in a DTMC. Now, we are talking about a CTMC. So, in continuous time, what is the probability of being in state being in state j at time t if I start in state I at time 0, alright. Now, Chapman-Kolmogorov equation relates Pij of t to Pjk of s and all that for s less than t, as we will see soon. Okay. So, I can write Pij of t as follows. Probability of given x 0 equal to I, which is by definition, which is equal to the probability that x of t equals j given, let us say x of s is equal to k, x of 0 equal to I. So, I am basically conditioning on the state at some intermediate time s to be equal to k times probability that x of s equals k given x of 0 equals I, this and then sum over k, all states, right. So, I am just, this is true for all s in 0 t, right. So, now if you notice this, by the Markov property I can drop that conditioning, right, because conditioning on the process being at time s being in state k, it does not matter where I started, right. So, I can write this as sum over k belongs to s p x t equals j given x of s equals k times what I have here, probability of x s equal to k given x naught equal to I is nothing but by definition it is p I k of s, correct. And what is that equal to? This also I can simplify. See, if at time s the process is in state k, right. So, the probability of the at time t the process being in state j, now this Markov property guarantees that this is equal to, it is as though the process starts at time 0 in state s, sorry, in state k, and then you are just looking at a time interval t minus s, right. So, just to draw this out, so looking at this is time 0, this is some time s and that is some time t. So, if x of s is equal to k, right. So, x of s equal to k, because x 0 is equal to I, right, x of t equals j, that is what I am looking at. So, at this point if I am at state k, it is as though I am starting a new process for this time duration t minus s, right, and I am, it is also time restarts at time 0 and I am in state k, right. So, by the property of this, by this Markov property, this just becomes, this guy just becomes p k j of t minus s, right. So, I get p I j of t equal to sum over k belongs to s, p k j of t minus s times p I k of s, okay. This is called the, so this is true for all s in 0 to t, okay, and this guy is called the Chapman-Kolmogorov equation for CTMCs. It basically expresses Pij of t, which is the transition probability at time t, in terms of transition probabilities at smaller times. Okay, and you can choose whatever s you want, right? S can be anything in 0 to t, and this equation is still valid. Okay. Now, as you can imagine, this Chapman-Kolmogorov equation just ends up expressing Pij of t in terms of Pkj of t minus s and Pik of s, which also we do not know really, right. So, we have just expressed Pij of t in terms of similar other quantities that we do not seem to know, right. So, it is not very clear that this is very useful, right. At least in the discrete case, we could inductively solve for Pij of n, then find out Pij of n plus 1 and all that using the Chapman-Kolmogorov equations. Here it does not seem obvious how we can even solve for this Pij of t, because what you have on the right hand side is also similar quantities that you don't know, right. Now, the solution to this, see, in the DTMC case you could just inductively do it, right, start with n equal to 2, then go to n equal to 3 and all that. In the continuous time case, in the CTMC case, this Chapman-Kolmogorov equations can be converted to a differential equation form. Okay. So, you can just look at very small time increments and look at the evolution of this Pij of t, okay, and then express, you can write out a coupled system of ordinary differential equations, which can ultimately end up solving for this Pij of t. Okay. That is what we will do now. So, there are two types of differential equations. One is called the Kolmogorov forward differential equation and the other is called the Kolmogorov backward differential equation. Okay. So, the Kolmogorov forward differential equation is obtained by taking this t minus s to be really small. So, what you do is send s towards t. So, if you look at this picture, you send this s, make this s approach t, right, make this s minus t really small, okay, and then you write out the Chapman-Kolmogorov equation for t minus s being really small and you get a set of differential equations, okay, that is called the Kolmogorov forward differential equations. Okay. So, essentially obtained by taking the limit s approaching t from below in the Chapman-Kolmogorov equation. Okay. So, let us do this. So, I am going to take t minus s is really small, alright. So, I am going to say what happens to let us see what happens to Pkj of t minus s. Okay. So, I am going to have t minus s really small, and what is Pkj of t minus s? Let us first consider the case k not equal to j. If k is not equal to j, Pkj of t minus s is basically the probability of going from state k to state j in a very small interval t minus s, right. So, this should be equal to the rate of transition from k to j multiplied by this very small time interval, which is t minus s, right. So, Pkj of t minus s can be approximated as Qkj, which is the rate of transition, times delta, with delta is here is just t minus s, plus little o delta, which is little o t minus s, alright. And for k equals j, right, you are just looking at Pkk. So, it is a probability of self transition, right. So, this will just become 1 minus nu, right. This is the probability of self transition, which is the probability that none of these exponentials actually fire in this small time interval. So, this will just become, so Pk equals j. So, I can write P, so maybe I should write like this, Pjj of k is equal to j now. So, p j of t minus s is equal to 1 minus nu j of t minus s plus little o of t minus s. Okay. So, you go fix this back into so sub into Kolmogorov Chapman-Kolmogorov equations. Okay. So, then what do you get? So, you get Pij of t is equal to sum over k not equal to j Pik of s times Qkj times t minus s plus little o t minus s, and then you have to take the term k equals j also, right. In the case k equals j, you get minus nu j p I j of t minus s. Nu j p I j times t minus s. Sorry, I think I made a mistake here. So, that is correct, and then I have this term sum over k equals j, in which case I should write p I j of s times 1 minus nu j times t minus s, plus you will have an order little o t minus s, which I have absorbed here, alright. So, now I can send take limit above, right. So, I am going to, before I take limit, I should just write this as, maybe I should do this a little later. So, I should do p I j of t minus p I j of s is equal to sum over k not equal to j p I k of s q k j of t minus s minus nu j times t minus s plus little o t minus s, alright. So, now you divide the whole thing by t minus s, in which case you will get, and then take limit, right. So, if you then you will have p I j of t minus p I j of s over t minus s is equal to sum over k not equal to j p I k of s q k j minus nu j plus little o t minus s over t minus s, alright. Now, take limit s approaching t, alright. So, that if you take in that the case, the limit of the left hand side will become d p I j t dt, alright, and that will be equal to, and this term will just this term will just drop off if you take limit t tending to s. This you will get limit s approaches t sum over k not equals j p I k of s q k j minus nu j. Now the question is, can I send the limit into the sum, right? If the summation is finite in the finite state Markov chain, I can certainly send it. In an infinite chain, you have to be a little more careful, because if you are pushing a limit inside an infinite sum, then you need some kind of a dominated convergence or some such thing. Nevertheless, you can validly do it as long as the nu j's, the transition rates are all bounded above, then you can send the limit inside. Okay, this you can show. In any case, for a finite chain, you can definitely send it inside. Okay, so we will pretend that this is valid. So I will just write this as sum over k not equal to j pi k of t q k j minus nu j. Okay. So I have, so for each I j, right, I can write this differential equation. All right. So these are coupled. So I want to find out pi j of t. I have written down the differential equation for pi j of t in terms of other pi k's, and similarly I can write t d pi k of t is equal to whatever, right. So I have this coupled system of linear differential equations. These are linear differential equations which I can solve for pi j of t. All right. So this is called the Kolmogorov forward equation. Kolmogorov forward equation. So to just show you a simple example of how to use this, if you just take this kind of a Markov chain, let us say this is a CTMC, in which, so you can think of this as an MM1 queue without any ability to store a customer. All right. So you either have one arrival like a Poisson process of rate lambda, the customer gets served and leaves. There is no further possibilities for any arrival. All right, any arrival, if you will, just gets dropped if the server is busy. If not, the person gets served and leaves. Okay. In this case, it's easy to check that q01, basically q01 is lambda, q10 is mu. So the question is, can we write down p01 of t equal to what, right? P01 of t is simply the probability that x of t is equal to 1 given x of 0 equal to 0. So I start the CTMC, this queuing system starts empty, and then I am going to look at the probability that there is one customer in the system at time t, from finite time t, right. I can of course write out the Kolmogorov differential equation like so. So I can write d p01 of t dt is equal to p00 t q01, which is lambda, we should write q01 minus p01 t nu 1, that is equal to p00 t lambda minus p01 t mu. All right. Now also p00 t is equal to 1 minus p01 t, right. So I can, the above differential equation just becomes d p01 t dt is equal to lambda times 1 minus p01 t minus mu times p01 t, right. And I can solve this to write, this is just a very simple linear differential equation, and so p01 t and I also have the initial condition that p01 of 0 is equal to 0, right, because the Markov chain is starting at state 0 and time 0. So I can just solve this differential equation very easily, and I get lambda over lambda plus mu 1 minus e to the minus lambda plus mu t, right. So this is great, right. So I have the probability that the Q has one customer at time t is given by lambda over lambda plus mu 1 minus e power minus lambda plus mu t. Of course, after a very long time this goes to lambda over lambda plus mu, right, which is the steady state probability that there is one customer in the queue. But this is true for every time, right. So, if I want to know what is the probability that there is one customer in the system at time t equal to 2.5, I can find out, right. So, that is the nice thing about this Kolmogorov equations. Well, as you can imagine, this is a very simple example for two states. Things become a little more complicated if you have multiple states, right. You will have a coupled system of linear differential equations. But you know, in the ODEs, coupled ODEs are widely studied as a branch of control or just ODEs. So there is enough literature on this. Once you write down the forward differential equations, it's a well understood mathematical object. In more generally, we can write the Kolmogorov forward equations in matrix form. So, for finite states. So, what you do is you have the matrix of, so let us say P of t is a matrix which is the matrix of Pij of t, alright, and let matrix Q be equal to the matrix of minus nu 1 minus nu 2 dot 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 minus nu, let us say minus nu m state Markov chain, and then everywhere else you have q1 2 q2 3 and so on. Okay. So, basically this guy has qij in the ith position, except that the negative the diagonal elements are all negative minus q's, minus nu's, minus nu i's, alright. So, what you have is that this q matrix has row sums equal to 0. If you remember, all the qij is sum to nu j, right, and you are putting nu j at the jth diagonal position. So, this is a matrix which has all the row sums equal to 0. Okay. So, it is a non full rank matrix, it has an eigenvalue 0, and this for this with this q matrix notation you can write down the forward differential equations as dpt dt, which is the matrix, is equal to P of t times matrix Q, right. So, this is the general form of the Kolmogorov forward differential equations. Now, we can also write out the Kolmogorov backward differential equations. You know, I do not want to spend too much time on this. So, the Kolmogorov backward differential equations are obtained by taking limit s down to 0 in Chapman-Kolmogorov equations, and that leads to the equation dPij dt. If you do a similar calculation sending s to 0, so you write down Pik of s as Qik times s plus little os and all that. So, you get dPij dt is equal to sum over k not equals I Qik Pkj of t minus nu I Pij of t, right. So, these are the Kolmogorov backward equations. And in matrix form this becomes d pt dt equals q p of t, alright. So, this the backward Kolmogorov equation looks almost the same, except the q and pt are on the right hand side, they are interchanged, okay, but the left hand sides are actually just the same, right, it is just dpt by dt. So, which shows that the matrix P of t, which is the matrix of the Pij of t, commutes with the rate matrix Q. This Q is called the rate matrix. So, this Pt matrix and Q matrix commute, alright. So, which is actually a somewhat non-trivial observation, and that comes very for free from just looking at the Kolmogorov backward equations and the forward equations. Anyway, these also you can solve, these are also coupled linear differential equations. So, bottom line is that these for finite state Markov chains, especially if you have small number of states, you can just solve these differential equations to find the probability that you are in any time at any finite time t, the probability that you are in state j, given that the CTMC started in state I, like we did for the toy example of just 2 states. Any finite state you can do, alright. I will stop here.